a research fellow at Johnson Matthey and leads James' research activities at Harwell, and is also responsible for corporate analytical teams in NMR and XPS at the Central Research Facility at Sonning Common. He's got quite a wide and broad career, and I guess many people on the call will know him. So he was going to talk to us today about developing new characterization capabilities. And so I'll hand over to Paul to take us through his talk. Thank you.
James, thank you very much for that very kind introduction. Can I just check you can see my slides okay?
Yes, I can. Yes.
Right, excellent. So one of the things I want to talk about this afternoon then was just a little bit of this is about how we do characterization. Many, if not all of us on here are familiar with the concept of characterization and what it's trying to do. I guess what we talk about less often is how we do this. You know, you can imagine it's, you know, you buy the machine, you put it in your lab, you use it, but often there's a space for collaboration, and this talk really, is about collaboration and how collaboration works. Oh, right, okay. So a little bit about Johnson Matthey. So Johnson Matthey's main interests, we can group them together, 3 areas. Firstly, cleaner air, and this is one of the areas that many people encounter Johnson Matthey. So this is catalysis for emissions control, for instance, on cars, on heavy-duty vehicles, and so on. Catalysis, very large part of this. Our efficient natural resources business as well, major user of catalysts, whether that's sort of petrochemicals or other basic commodity chemicals as well. For instance, you know, producing green jet fuel, blue and green hydrogen as well is involved in that area. Lots of involvement with catalysis, but also process engineering as well. Our healthcare business as well, focused on many areas around healthcare. There's a big technology aspect, but there's also a sort of like a API aspect where you're making compounds, and often catalysis is used in that area. So many of us, if not again most of us, are already interested in catalysis, which is why we're here on this call. So I almost don't need to tell people why you would want to look at catalysis, but it is just worth looking at the impact. When we work in catalysis, we often forget about the bigger picture. And so many, I mean, the figure quoted is 90%, but so many industrial processes are catalyzed at some point in their value chain. Massive impact on global GDP, major areas of impact all the way through areas of human life, you know, transport, healthcare, energy, everything. So really important enabling technology, and that's quite a good concept to keep hold of. The graph at the bottom here just shows exactly the power of this. This is a catalytic converter on a vehicle using Euro 5, which was one of was a previous standard used in Europe. And you can see the blue line, the area under the curve, the blue curve represents with the catalytic converter the amount of tailpipe emissions compared to the hash line, which is without the catalyst. So already you can see the power there. And these are some pretty toxic things that are being stopped here, like CO and nitrogen oxides and so on, particulates. So big impact for catalysis there. When we look forwards, many of the world's big problems are accessible to catalysis, and in fact, catalysis will probably play some part in the solutions to these issues. Climate change is in the news. You know, we've got commitments to net zero. We're already talking about circular economy. We're talking about more efficient routes to making chemicals and materials and products as well. So big impact for catalysis there. Population growth, improvements in global health as well are also drivers. Urbanization, and also diversification of feedstocks, which is, I guess, it's something that we don't often talk about. But you know, feedstocks are changing, and there's a strong geographical nature to those. So, you know, what you might run your process on in North America isn't necessarily what you might run it on in China, for instance. And of course, digitalization and AI is having ever more reaching impacts in science as well, but both in academia and in industry as well. So in terms of the science that's coming behind that, you know, seeing the unseen sounds very Rumsfeldian, I suppose. But it's a key aim for all of us, really. You know, I think we all have this worry that we're not seeing the whole picture in a catalyzed process, and we always want more. We want to see more about what's going on, and I think that's a good thing, and I guess that's one of the motivators for why we do the work that we're talking about here today. Obviously, want to measure in situ. It's fine measuring a material before a reaction or even after the reaction. What you want to know about is what's happening during the reaction. When it's doing its thing, when it's being a catalyst, when it's doing the conversion of your reagent into your product, you want to know what's happening on the surface. Strong link to modeling, in silico design of new materials, linking that to ever finer control of atom manipulation. And again, we've got the AI coming in at all these strands here. So this is a kind of classic materials optimization sort of schematic. Many people use something like this, whether formally or informally. You know, at some point we may start with modeling. We've got various modeling techniques coming in. We've got preparation technology, so we're making something on the back of the model. We may characterize what we've made, and then we might want to do some testing, and then we might want to feedback around here. Depending where you start on this, I guess is a personal point of view. Whether you want to start with your modeling as predictive, or whether you want to make something and then characterize it and eventually understand how it works because of modeling, is another way of doing it. Personally, I suspect the modeling-driven approach probably yields a lot more benefits. So, the importance of characterization. So characterization in an industrial concept is absolutely crucial, especially for the development of new products. Really, we want to know where the atoms are and what are they doing, and how does this relate to performance. All the time in industry, customers come up to you and they'll say to you, very good, we like this current product. We want the next generation to be X% better, Y% cheaper, and to last, you know, Z days longer than this one. All the time they want that. And the only way you can answer questions like that is by understanding more about your materials and understanding what the function is of all the different components. And then once you have that knowledge, you can then build and improve for the next generation. And often multiple techniques are being used now to gain that complete picture. There was one time when you could probably get away with one or two techniques just to understand the material. Now it's multiple inputs from different specializations. So, you know, we're all talking about a catalyst, but what do we mean by a catalyst? So again, it's a perspective view here. If you're a DFT modeler, well, then you're probably already right over on the right-hand side of this picture. You're thinking about the atoms and the surfaces. If you're a chemical engineer, you're probably quite far over on the left, thinking about something that has large macro-scale structure, maybe even the whole reactor itself or something like that. You know, I guess we all have a view all the way through here. So we've got, in this case, it's a monolith, coated monolith with a catalyst. The structure all the way down to the atoms, and you can have an effect on the reaction all the way down here, whether it's diffusion and mass transport effects over here, or whether it's adsorption effects over here. And if we sort of translate that into, you know, into an effect, looking at the different components here, in that example, it was monoliths. So we've got things like monolith wall thickness effects. We've got aggregated structures coming down towards crystal sizes, metal support sizes as well. And then if you're looking at zeolites, for instance, or even single site catalysis. So all of these things can play a role at either different times during the reaction, or perhaps, you know, at different scales, because, you know, they're all important. So at this point, I just wanted to talk about the Catalysis Hub. Catalysis Hub has been a really good endeavor in the UK. It's brought together many universities working on common problems and helping to solve societally very relevant challenges. spread out across the UK, and Johnson Matthey have been key supporters of this, both in phase 1 and in the current phase 2. It's also been a key enabler for industry to help us work more closely with universities and also with the national facilities at Harwell, who've been closely involved in many of the projects. So it's a good vehicle to get involved in developing new characterization capabilities. So thinking more, I guess, more precisely about Harwell, which for those not in the UK is not too far away from Oxford. It's not a million miles away from London either. It's in the sort of southern part of England. UK's premier national science facility, so it has a synchrotron and it has a neutron spallation source and also an advanced laser facility as well. There's a lot here to attract industry. For us, some of the drivers here are listed. We're very interested in developing new characterization techniques, but also interested in things like in situ measurement, interested in novel environments, but also developing complementary techniques. And obvious ones are when you're combining X-rays and neutrons together. For instance, universities are absolutely crucial in making all of this work. It's kind of a triangle in a way between industry and the national facilities and universities, with everyone bringing something and making it happen. So just a thought about Harwell. So this is a nice environment, and there are a number of sites around the world actually that are built on similar principles. So this isn't a UK specific thing. There are sites in the US and in Asia as well, and in mainland Europe as well. Very good at encouraging collaboration, step out disruptive innovation, but also across traditional knowledge boundaries. World-class facilities. Many of the techniques you get on this sort of campus are completely unavailable to industry. You're never going to have your own synchrotron, for instance, in industry. So you definitely need to go somewhere where specialists can run and maintain and develop indeed these techniques. Harwell, we've got the mid-range XPS facility, which we've had some very close links with as well. All of these facilities are very open for industry to participate in research. And the scientists on site they're really passionate about what they do, and they really like to hear about industrial challenges. I've never heard anyone at Harwell say no, we can't do that. It's more about a yes and conversation rather than a no but. So very positive conversations about how experiments can be improved and how you can get the knowledge that you want from that. And finally, very good EHS culture, which in industry is paramount importance to us. So I basically in the second part of the talk, I've got a couple of examples of case studies where PhD projects supported by Johnson Matthey have been placed with a number of with the university, and then obviously got the link to the national science facilities at Harwell. And really the aim in each case was to try and understand more about different materials, different catalysts actually, that were relevant to JM, but also relevant to the community. And that you've also got that sense of capability build where you're enriching the community as well through this sort of collaboration. This first one is with the University of Glasgow, and you had David Lennon was talking earlier. David Lennon's been a very, very strong collaborator with Johnson Matthey, going back quite a long time now. We've done a lot of very good work together. This particular work has come from two students at Glasgow, Andrea Zaccario and Alexander Hawkins, but also Stuart Parker has been involved, and in Silverwood, and my colleague Nathan Barrow from Johnson Matthey, and also Russell Howe. This has been looking at ZSM5 reactions and really the effect of steaming on ZSM5 and how it impacts on particularly propene behavior. But there are a whole load of papers that have come out of this project, which are very interesting and definitely worth looking up if you're interested more in zeolite chemistry. So ZSM5, very important catalyst. It's got very strong industrial relevance. Interaction of light hydrocarbons with ZSM5 is very important as well. Propene, we've got as a molecule we've been looking at here. Very interesting behavior for propene, and it's very relevant to a lot of petrochemicals processes that go on. Often under very harsh conditions, where often the fresh catalyst that you put in is not the catalyst that's actually doing the work under the working conditions. mainly because of the high level of steam in these sorts of processes. So here with this project, we've been looking at the effect of steam, studying the fresh catalyst and the steam catalyst, and trying to understand a bit more about what impact the steam has on the zeolite in this case. Here, very powerfully, bringing together infrared spectroscopy, but also with neutron techniques like inelastic neutron scattering and Quens quasi-elastic neutron scattering. And in Johnson Matthey, we're very interested in this sort of combination. There was a time, maybe beyond 5 years ago, when we didn't really do very much with neutrons, but now neutrons are a very interesting technique for us, and it's very nice to see this work being done and the combinations of techniques here. So here we've got a sort of conventional characterization view of the fresh and the steamed zeolite. So the blue line on the left, this is the IR spectra, the drifts for the fresh catalyst, the activated ZSM5 is the blue, and then the red one represents the steamed. So straight away, the sort of obvious thing that you get from the IR is the sort of massive decrease in the Bronsted acid groups, the OH stretch for that one. There are some effects on other areas, but that's a kind of a first big standout thing that you see. Ammonia TBD supports this, massive, again, a reduction, 92% in this case, reduction of silanol groups, but also big reduction in Bronsted acid sites. So you're giving this material a hammering, basically, under the steaming conditions. Again, NMR, a very powerful technique when looking at zeolite materials. So here we've got a solid state aluminium NMR, which shows this this loss of the ALOH signal, which, yeah, again, it's very supportive of the IR. It shows this damage to the zeolite by steaming. So now we're going to move on to INS spectra, inelastic neutron scattering. Basically looking, this is a steamed zeolite, and what we're doing is looking at the effect of temperature on the INS spectrum once it's been dosed with propene. So what's really interesting for a start is that in the fresh material, you see reaction of propene in fresh ZSM5, really low temperatures. Around about 225 Kelvin, you've got the propene reacting, starts to do oligomerization, and then it goes on to kind of form all sorts of things, higher chain numbers and so on. In the steam material, really you don't see very much until beyond 290 Kelvin. So in the INS spectrum here, which was recorded at ISIS at Harwell, you can see this quite nicely actually. So where the dotted line is on the right, this represents an increase in this methylene rock signal over here, stretch, which is indicative basically of that oligomerization taking place. And then over here, you've got several peaks which are all corresponding to the propene, and you start to see these decreasing with time on stream. This is a strong sense that the catalyst has become deactivated, and that it requires more temperature basically to do its thing. Very, very nice quality of data you get from the INS. So it's clearly complementary to the IR, but it obviously shows things that the IR can't see. So there's a very strong role for INS in probing this sort of reaction. The Quens was done on these materials as well. Quens is a very interesting technique, and really it tells you about diffusion of molecular species. And in this case, we're looking at the propene diffusion through the zeolite. So you've got the curve for the fresh material, which is the blue line, and then the steamed material is the red line. And what's interesting is the red line shows much faster diffusivity of the propene through the ZSM5. So you've obviously impacted on the pore structure in some way, even before reactions taking place. I mean, we know from the earlier data from the INS that reactions happening around 290 Kelvin. But all the way back here, you can see even before you've got reaction taking place, you can see that there's an impact on diffusion. So obviously massive structural change there. So, as I say, this was part of a larger program looking at zeolites in sort of methanol transformation, but also hydrocarbon transformation reactions. Very exciting research. A lot of very high impact papers came out of this. And you know, in this particular work, we've been looking at steaming. There's a lot else that we've done that's relevant to this. And from the JM point of view, it's really brought us much closer to the use of things like INS and Quens in an industrial setting. Which is very powerful. So you've got that technology transfer aspect there. So the last case study I wanted to do, this was another PhD student at Harwell. This is Ellie Dan, who is a PhD student with Peter Wells, who is Diamond and University of Southampton, but also Richard Catlow and Andy Beale were involved, and then several colleagues from Johnson Matthey looking at this. This was an early hub project. This took place in Hub 1, and it was looking at developing in situ environments for synchrotron methods. So on the next slide here, you can see what we were trying to do with this project, trying to combine EXAFs with drifts simultaneously. So we all know about EXAFs. We've got some very nice element-specific information from the Zane side of things. We can see something about oxidation state. Obviously, EXAFs giving us coordination geometry and local coordination environment as well. And then from the drifts, we've got that nice sense about speciation and surface reactivity. So here's an image from B18. This was the setup being used at B18 on the beamline there. And on the left is the modified Harrick cell, where we, I guess this is where we started on the project. And then Ellie did a great job using this to record the first beam times, acquiring data and so on. There's some really good strengths about the Harrick, but there are also some issues as well. It's quite hard to measure transient reaction data, for instance, in something like this because of the large gas volume. So what we were interested in doing was developing something that was that enabled more transient measurements. And as I say, you know, Ellie and the team did a tremendous job involving a lot of design and a lot of prototyping in the project, and it resulted in this like flow cell. It's a flow cell that measures you can do transient reactions. So you've got something that's X-ray transparent, but you can also get IR an IR laser through here as well. And then basically along the bed, you can take measurement at any point along the bed from the inlet to the outlet, and then obviously you've got a mass spec on the back looking at this. So on the right-hand side over here, we've got some, I'm too fast for myself here. You've got some examples of, you know, slices taken through the bed. And this particular one is looking at CO oxidation over palladium catalyst. And you can measure the mass spec signal for oxygen. You can see CO on the drifts. You can see the palladium edge, white line edge on the ZAFs as well. And you know, we had some really nice papers out on this, looking at things like the classic CO oxidation, the oscillation of that on palladium, and able to show that actually you see the effect of that on the palladium surface state as well, which was something that hadn't been reported before. So this is really useful. It starts to bring you really close into the catalyst to see what's going on with that. So that's I've come to the end of my talk there. There's so much more that I could have said about collaborations, but collaboration is really important, and I think there's a really nice sweet spot where everyone can get something out of collaborating. And yes, it's something that definitely has my wholehearted support. Really big thanks to all of the parties that we work with at Harwell, especially for this project, for the slides I've given here today, to University of Glasgow, University of Southampton as well, and also Queen's University of Belfast for their support with Ellie's project. And thank you for listening. Thanks for the opportunity to talk. And yeah, very happy to take questions as well.
Brilliant. Thank you, Paul. It's a very interesting final talk, and brings the talks of the session of the meeting to a close. I think we've got a bit of time for one or two questions. So if people have got a question on that, then please type it into the chat or the Q&A box. We've got one question that's come in already. Thanks for the nice talk. What is the silicon to aluminium ratio of the zeolite? What are the steaming temperatures and duration?
So David's on here, but he might want to correct me. The details are in the paper that's cited. I believe it's 30:1 for the silica to aluminum ratio, and the steaming temperature, I'm not sure. I'll have to come back to you. It will be quite high because in those sort of petrochemical processes that we were looking at, it was at 700-800 C. So my first guess is about 700-800 C, but actually I'll come back to you with the details on that. David, I don't know whether you can comment.
Yeah, absolutely correct, Paul. Spot on.
Very good. Just waiting for any other questions to come in. I've got one kind of quick one, which links back to the early slides you talked about, James, sort of interests and areas of research, but it was really about kind of data, and I guess some of these techniques, certainly XFs or Quens or different types of techniques like this, they can generate huge amounts of data. Have you had any kind of feelings or thoughts about how sort of big data fits in with sort of digital and AI and all those sort of things? I know it's something that we're kind of looking at as well, but do you have any kind of perspectives on that?
Yeah, I think that's a really good question, James. And it only becomes more of a nightmare when you start to look at things like tomography. If you look at the size of data sets you can get from XCT measurements, and that's before they become in situ, it's massive. This is a collaborative space. So there are people at Diamond and ISIS and synchrotrons around the world, indeed, and neutron facilities who are looking to try and get closer to on-the-fly data analysis, for different techniques. From an industrial point of view, it does become very rate limiting for how much work you can actually do using, say, a synchrotron. If every hour on the beamline takes you a week's worth of data analysis when you get home to analyze the data, you can quite quickly run out of people trying to analyze your data. So I think that there's a lot of interest and a lot of motivation for automating more and more of that data analysis process. So definitely something that we're interested in. Clearly, things like machine learning have got an angle to play here. It's early days, I'd say. I don't think there's any one-size-fits-all view of this, of exactly how to optimize data. But I've seen some really nice examples where people have chewed through some pretty large data sets and got some nice insights out of those. And again, this is driven by scientists. So these tools, the AI tools, are tools that scientists will use. This is not about replacing scientists with algorithms. It's enabling scientists to have greater reach, basically. So I think we'll see more and more of this. I think it's over this coming decade, it will be a journey on that, absolutely.
Brilliant. We've got a couple of questions coming in. Thank you for the interesting talk. Are there more ways to involve students who are interested in scaling up their work? That's a good question.
Yes, no, absolutely. And students are actually in a very strong position because by the end of their PhD, they become experts in a field, and actually they are the vehicle for technology translation into a company. So this is something that companies actually would want to encourage, is students getting more involved in. I mean, you can say scale up, but also the exploitation of the learning. There's also the skills that have been learned. For instance, if you're looking at, I don't know, INS or Quens, those things are not routinely used in many companies at the moment, but there are many companies out there who actually probably would benefit from those. And I guess the reason why they wouldn't do them is because they don't necessarily have the skills in-house. So, getting the translation through into industry is a big thing there. So yes, absolutely. And if you're doing a PhD sponsored by a company, I don't be afraid to be proactive and ask them for opportunities to either scale up or translate their work in, or even just come and speak to internal research teams and tell them about the work. I think you'll find companies are quite positive about that.
I'd sort of add to that and sort of say, I think a lot of the time people from industry are more than happy to talk about things and get sort of different perspectives from academic work. And so, yeah, just if you're at a conference like the UK Catalysis conference or whatever, then just go and have a chat over a coffee with people from industry. It's it's a good way to make connections. And if you're interested in careers down that line, then it's a really good way to kind of get your foot in the door.
No, definitely, absolutely agree with that.
I got a question from Mohammed here. What is the difference between in situ and operando characterization techniques when we are talking about catalyst characterization?
Well, I don't know if I should answer this with so many academics on the line. We might not get away tonight.
I was going to say, you better be careful how you answer that.
This is it. We could start a big argument here. So what I've always taken as the definition is that in situ is when a material is exposed to an environment like a gas environment or temperature or some sort of external force that you start to get a sense of it doing its work. Operando is when it actually is under its process conditions, whatever they are. So for instance, you might look at something like steam reforming. You know, actual steam reforming of methane, as done in industry, is running at 30 bar and 900 Celsius. Very few people are probably going to run in situ measurements under those conditions, but they might run it under 5 bar and, you know, at 500 Celsius or something, and then start to look at some of the effects. So you start to get that interplay between what's practically achievable in the lab versus how something is actually used in industry. And this is another dimension for scientists to consider in the same way that we really have to be thinking about the data that comes out of the different techniques and how to combine data, say from XRD and XPS together. We've got to understand the sort of the scope and range and limitations of all the techniques before we bring them together. And it's the same way with testing. You know, we should think about, you know, what is the final application? How is the material actually going to be used? And equally, how close can we get to that in the lab? And if you can't get close to it, well, does that matter? You know, have you already seen enough of the things that you need to see? Are you really only interested in, say, activation, or is it some aspect of deactivation that you want to study? And even though you're not strictly operando, you might still be able to actually use that technique because it tells you enough about what's going on. But using it with insight, I think, is the most important thing in a thoughtful way.
And maybe one final question that links quite neatly on from that. Paul, playing devil's advocate here, what proportion of results you presented were actionable? Did the data enable you to change a catalyst in a field to perform better? If so, how?
I mean, I think anyone involved in catalysis will know that it's a long game. You know, if you're dealing with fast-moving consumer goods industries, FMCG, you know, it's quite common for new products to arrive in a year and then be commercialized. In the chemical industry, it takes a lot longer than that. So it's more of a build, I'd say, in the chemical industry, where, you know, 5 to 10 years is not uncommon for new products to come through. What I would say is that both of these projects have led to a much greater understanding of these materials, the materials that were studied, and particularly over the whole range of their behavior. So, you know, and also it shows you that you need to understand more about in situ when you do the characterization. So I'd say there's a lot in underpinning science that's come out of these sorts of projects. And these are two examples. I mean, we've done many projects at Harwell and with the Catalysis Hub as well. And we've got value out of all of those. You know, have any of them directly led to new products? Well, probably not at this point. Have they supported Johnson Matthey teams, you know, who are developing products? Absolutely. Has the learning come out of them, you know, informed decisions that have been made about those products? Yes, yes, it has. So I think there's a case for value to be demonstrated there, absolutely, and I think we've done that. You know, once you start to talk about dollars, I think it's a lot harder, and this is a current debate in R&D, is how you relate R&D to sales, dollar sales at the end of the day. Everyone wants to claim their share of the dollars that are made on a catalyst that gets sold, and usually it's the sales team that claim most of it, you know, and then beyond that, it might be the development group who actually did the final bit of product development, or the operations team who made it. You know, but what about the R&D teams further back, or the university collaborators? You know, surely it was a team effort. And yes, I think everyone has a hand there to steer the ship, but it's quite hard for any one group to claim that they were the one that had the success.
Very good. And one final question before we wrap up neatly on time. Hi, Paul. Very nice talk. I was wondering, after the characterization calibration such as XAFs, drifts, you will get the information about the surface absorption, oxidation state, coordination. Then what is the main purpose of this characterization information? does it help, or will it help give you some idea to design or fabricate the catalyst or the interface between the metal and the support when you come back using these results?
So maybe I could answer this in a slightly holistic way. One of the things that I've seen over the years is that the more you understand about the chemistry in your areas, the more you can make informed choices about the way you make your catalysts or how you improve them. So, for instance, you know, and I think David touched on this when he was talking about the nitrobenzene hydrogenation. You know, understanding what's happening with your alumina, for instance, tells you a lot more about the sites on the catalyst. Understanding what about your precious metal or whatever the salt is, its chemistry in solution tells you a lot more about the catalyst. And all of it is all stuff that can lead to improved products. It gives you a greater toolkit to actually improve things. So often with these capabilities, what you need are things that are generally applicable rather than just one shots that can only be used for one reaction. So in both of these cases, for instance, what we've got here is a developed capability that could then be applied in a number of areas. And all the way through that, so whether you're making materials or whether you're testing them being used, you know, you can start to use these kind of techniques to look at that. So yeah, I think there's value there, and you know, each thing, the IR, the ZAFs are providing something different. Sometimes actually having corroborating evidence from two different techniques is quite a good thing. So if you see something from XAFs, it's really nice to see the same thing or similar from IR, and then to be able to compare them, especially if you're relating it into modeling. I think that's no bad thing, actually.
Very good. No, well, that's brilliant talk, and thank you for going through the questions. I think that brings us very neatly to 4 o'clock, where we sort of wrap up. I hope this webinar session has been useful to all the audience. Quite a number of areas around applied characterization and characterization in catalysis. So hopefully it's been an interesting afternoon. It certainly has, and I've learned a lot from my perspective. I'd just like to thank all 4 speakers again for their help and agreeing to give the talks and spending their time answering the questions. It's much appreciated, especially people from industry sort of sharing some of their potentially sensitive work. It's very nice to hear from them. And I'd also like to just thank Josie and Corinne for setting up all the IT and putting it all together and making it all work. So I think there's been a few messages in the chat about future events. I think there's a webinar for PhD students on catalysis, and I think there's also 1 or 2 other events coming up. So please have a look at the UK Catalysis Hub webinar website for events going forward with that. But go for it, Josie.
In that webinar next month from some of the students in the hub, there is a talk from Alex Walken, which has some of the work that Paul referenced today. So if you'd like to find more about that project on the operando, on the studies of ZMS5, that's great. And we've got some talk on operando studies as well in that webinar.
Brilliant. So yeah, thank you everyone for attending and for all the really great questions all the way through. So as I say, I hope it's been a really good afternoon for everyone, and look forward to seeing you all again